this one, and in this one, I'm going to use Google Colab. And I've got it all ready to go. In fact, I've already got it. So you can use any Python environment, but I like to use Google Colab when I can because, of course, every student can use it no matter what kind of computer you have. So you log into a Google account and go to colab.research.google.com. And you can now execute, like we did before, if you put an exclamation point in front, you have a bash command. Otherwise, it's a Python command. So here, first thing you have to do is generate an RSA key, just like we did it before. So you just generate, here, using 512-bit keys again, just like before, just to make it simple. And so you make a key, and you can see it here. And here's the key in the PEM format, a blob of base 64. And here you can unpack it with the OpenSSL RSA command. And here you see this is N, this is E, and this is D. And here's P and Q. And there's other things. So that's what these are. We've seen that before. We've done all that in a previous project. So you can find these essential numbers from the, now this is the private key, which is big because it contains all these values. All right, you can also generate the public key, same as you did before. You use this RSA input out, pub out. The pub out command makes the public key that goes at the private key, and the public key is much shorter because you can unpack it. All it has is N and E, that's it. So it has just the first two fields here, N and E, and it doesn't have any of this stuff, which of course all these are secret. All of them are related to P and Q, and so you have to keep all of them secret. If anybody was to learn any of them, they could break the encryption. So now you encrypt this way. You can make a message and just turn it into hex and look at the length. So here's my message in hex. This is capital H is 48, a small e is 65, and so on. I've just taken the hexadecimal values of those characters in ASCII and strung them together to make a long hexadecimal number. And so now I can take that number. Okay, now here I have to have N, E, and D. And what I have to do is I had to bring in the values from here. So I had to go back here. Here's N, for example. And what I had to do was take this and put it in a text editor because I have to clean it up. For some reason, they put colons in it and all that junk. So you have to get rid of that. You have to get rid of colons and replace them with nothing. And then you have to get rid of this, carriage return in 5 spaces, and replace that with nothing. There. And replace all of them. There. Now you get one long hexadecimal number without the junk in it, and that's the format you need it in here to get it into Python. You just take the integer of that long number, comma 16. That'll interpret it as a base 16 number and make it into a big integer. And you have to do that for both N and D, and also for E, although E is always the same. That number, like I say, everybody uses 65537. They've decided that is generally the best number to use for E. So you'll have to, when you generate your own key, you'll have to go back here and get those two values, N and D, and get rid of the colons and carriage returns and spaces to feed it in here to get them into Python where you can use them. And now we can take our message is going to also be interpreted as a number in base 16. That XE is this number here, just the ASCII values of all the letters. So you interpret it as a big number. And now you take X to the D mod N with this POW function, which is, if you do it like X star star D percent N, it will take forever because that will actually try to multiply it. This POW function is smart enough to use this successive square thing to go fast. Yeah, the POW function will do it fast. The other function will never get there. And so then you have to take the output of that, express it as a hex value, and print it. So here's the hexadecimal value of the encrypted message. And see, it's much longer than the message, and this is very common with RSA. The key is very long, the message is usually shorter. And that's why, we really should be padding it. What we're doing here is textbook RSA, which has all those flaws we talked about. So anyway, now we have a numerical X. X prime is the, I think that's the encrypted stuff. S to D, oh, the signature, we're making a signature, that's right. So we're taking the signature to the E mod n, and yeah, S is X to the D mod n, so S is the plain text. Or signing, okay, we take the plain text to the D mod n, we're making a signature. That's what this is. We take it to the decryption key so anybody can verify it with the encryption key. So that S is the signature, and now this is verifying the signature. So the person who receives it will take S to the E mod n, and they'll get the X, this is the X prime from the signature, and then they'll just take the message and see what that is, and here's the message recovered. And okay, and I think the point is, right, in this case, XPH is hex, print X. Yeah, here the XPN is printed actually in decimal, so you can't compare these and see they're the same. I think I'd be better to have a hex here. Seems to be a defect in my instructions. I think that would be better. Oh, there it is. XPH is hex of XPN. Okay, it's there already. Never mind. And so here's the message. All right, let me read my instructions. I forget what that X prime is supposed to be. The X prime is bothering me. They're verifying the signature. You take a numerical X prime. I can't remember what the X prime is. XPN is S to the E, okay, S to the E mod n. This is the thing that is supposed to give me back the original message. That's why I think it's called X prime. It's supposed to equal X. Okay, so this number, X prime, 1614, should match the encrypted message or the plain text message, which would be 48. That's why I'm not understanding it. Nope. But I think that's because it's in base 10. Here it is. Okay, here it is. Here we are. Here's the, oh crap. I hate it. There's stupid mouse gestures that do stupid things on my screen. All right. Okay. What's going on? This is the verification where you take the signature to the E mod n. This is in base 10, so it's useless. This is in base 16. And that is the plain text message in ASCII, 48656C. That's what we had up here, 48656C. So this is just the ASCII version of the message, and it matches this. So that's what proves the signature is right. When you take the signature to the E mod n, you get back the plain text message. That's the point. Okay, so now I feel better. So that message is signed. And here's how, now here's the problem. Here's the forgery attack. This is called the existential forgery. What you do is you just guess a number to be a signature, and you can create a message that signature will match without knowing D. That's the trick. So I pick the signature, then I calculate S to the E mod n, and these are both public numbers, E and N. So I make a signature, I'll just make F. It's ridiculously short, but it's a valid number. So here's my signature. Now I take S to the E mod n, and I get a hexadecimal string, which is just garbage like this. And then if I turn it back into ASCII, it's just random garbage. The message is unprintable junk, but the message mathematically fits the signature. So I can forge a correctly signed message without knowing D. That's one of the many flaws of unpadded RSA. With no padding and no hashing. Remember, either the padding or the hashing would have fixed this. If I had to sign the hash, I think I'd have a problem. But anyway, so that's the problem. And so now you can show that it does in fact match. You can create an existential forgery attack. So that's what's going on. And so now you've got, you're going to sign something with your name, and then use your name as the signature. And then there's another one, you get a lot of points by actually making another one signing with a correctly signed message starting with ABC. There's a couple of tricks here. So try this stuff if you like. That's the existential forgery attack. And that's what I wanted to show you. And that uses up our time.